We've been talking about vectors for a little while now. I've posted quite a few videos about this, and one of the things that we've worked with a lot of are converting back and forth between component form and direct notation. We've found magnitudes and directions, kind of working the other way to find those x and y components. And what I want to talk about today is how to work with more than one vector. We're just going to go over the basics here, and then I'll kind of separate a few smaller videos with just quick examples as opposed to rambling for 20 minutes like I'm prone to do if I get carried away. In this video, though, I just want to make a note that we have discussed the fact that a vector, while it may be given in direct notation, is often given in a form like this, where we have our x components and our y components kind of set up or situated. In fact, I don't really necessarily need the hats in here since those are mostly kind of magnitudes. The direction's kind of built into them. What we're going to do today, though, again, is what I said was we're going to add a second vector. And so let's just call it W for the sake of this one. And since I already used the little hats above, I'll be consistent here. The very idea of vector addition is actually pretty straightforward. The mechanical side of it is the simple part, at least. To find the vectors v plus w, all you have to do is combine their x forces. So we're going to add vx and wx and combine their y forces. And that's all there is to it. This is not something that is actually all that strenuous or complicated. The hardest part of a problem, I think, is just persevering and pushing through the layers they may add to it. But in general, this is the idea. In fact, this would work for however many vectors they wanted to add. Suppose they wanted to have 10 people all holding ropes pulling in the same object in a bunch of different directions. If you could find all of their component forces, then you would have 10 different x components to add up, you'd have 10 different y components to add up, and then you'd be able to kind of squeeze together the resultant vector, what would actually happen to the object they're pulling on. So this can get pretty complicated, convoluted, or at least tedious. That's probably more tedious than difficult. But in general, this is all you're going to have to do. The biggest thing that I want to point out is they will not always give you component form. Make sure that you are able to work this stuff out, remembering that to find your x components, all you have to do is take the magnitude of the vector you're given, multiply that by cosine of your direction angle, where theta is measured from the positive x-axis and counterclockwise. We have to make sure we're being careful about that. Otherwise, the formulas that I'm writing down are basically useless, at least most of the time. There are some rare cases where if you goof up, maybe it'll still work. But in general, we can find these things this way. Same would be true for W. You just use Wx and the magnitude of W instead. It's important that you're able to work through that. And in fact, we'll just do the most basic example here of let's just combine two vectors. Let's say u is 5, negative 6. You gotta love math where you can say u is and still be grammatically correct. So u is 5, negative 6, and v is negative 3, negative 5. We're going to go ahead and find that u plus v, in a very straightforward fashion, is 5 plus negative 3, so let's just write it that way first, and negative 6 plus negative 5. Now I'm getting a little carried away with parentheses, I'm being a little excessive here, but it's very important to watch out for negatives with these problems. This is one of the reasons why this works out in such a nice way, is that it takes into account all the different directions that are being affected. The negatives and the positives tell me left and right, up and down, and that sort of thing. And so, like here, we can see that both vectors are pushing down, so we're going to have a very strong downward force. But here, this one's pushing to the right, but this one's pushing back to the left a bit, so we're not going to go that far to the right in general. So the idea is whatever resultant I would get would only move a little bit in the right-hand direction, but it would move a lot in the downward direction. And so I know that if I combine two forces of these magnitudes, it would result in a force like this. So you can imagine that if two people were trying to slide a box across a room and they were pushing in those directions, he was pushing to the right and down, she was pushing to the left and down, then you're going to see that that box is going to barely move to the right at all. Maybe they don't really need to go too far. Maybe there's a wall there and they're just barely pushing it up against the wall. And then they're sliding it really hard in the other direction together to get that leverage to push it really far in that direction. So be mindful of your positives and your negatives. Be careful with them. But notice again, very straightforward here. All I did was add up some numbers.